This is the video presentation for the dual operating modes of in-context learning. The roadmap, including motivation, task retrieval and task learning, theoretical framework for in-context learning, and analysis and phenomena. I will start from the motivation to introduce the in-context learning and the mysterious phenomena, and I will put a small title in the top left part of the slide. So what is in-context learning? We know that we can use LLM as predictor. For instance, we can throw the question to language model, and the language model will give us answer. But sometimes language model will give us wrong answer. So in order to improve the accuracy, we can provide extra examples. For here, we can provide 2 examples in addition to the question. And in that case, the language model can increase the accuracy. So the in-context learning is that we provide extra in-context example to the question and let the model improve its accuracy of the prediction. So we can expect that the error rate will decrease with the increasing number of in-context learning example. So this is what we expect. However, some mysterious phenomena happen in the literature that the error rate increase first and then decrease, although we use correct label. So this phenomenon is first introduced in the GPT-3 paper. They show that the one-shot accuracy is lower than the zero-shot and few-shot. So the question is, what happens here? Why we observe this weird phenomenon? I need to introduce the task retrieval and task learning, and then use them to give hypotheses for the weird phenomenon. So let's see some example first. Consider the following linear question, and I will ask the language model ChatGPT 4o to give me the answer directly. So we have 4 equations, and it's a linear question, so we have 4 coefficients. So ideally, we can solve the question. And the language model, we hope that the language model can give us the correct answer. So here, the ChatGPT will give us the correct answer. The return is the answer is 50, and we know the coefficients are all 1. So the summation over the 4 number leads to the correct answer. So the answer is just 50. So I will name this task learning because the model can solve the question purely based on the in-context example. Let's see another task. We only have 2 equations here, and we still ask the ChatGPT the same question. In this case, the ChatGPT will still give us the answer is 50. So the question is, we only have 2 equations, but we have 4 coefficients. So the question is ill-defined. So I named this task retrieval because the answer is heavily based on the pre-training prior. So I will use the 2 modes to explain the phenomenon. So at the blue region, under certain case, task retrieval will happen first, but we may retrieve our wrong task, and this lead to the increasing error. And at the second stage, as the number of in-context example increases, the task learning will become the main effect. So the language model can learn the function from so many examples and finally make the loss decrease. The question is that, can we have a mathematical framework to show this phenomena? Let's go to the third part, the theoretical framework for in-context learning. This part including pre-training phase, including data distribution and minimization object. And after we pre-train model, we go to the second phase, the in-context learning phase, and we will do in-context inference. In order to do pre-training, we need to generate pre-training dataset or pre-training sequence, and the sequence follow xy, xy until xk, yk. So we assume the pre-training data follows this in-context format. And in order to generate this sequence, we first generated a task. We generated mu and w from some prior, and the prior is defined as a mixture of Gaussian. So pi m is the mixture weight, and the p mu w condition on the mth component is a Gaussian. And then we sample x, follow a Gaussian with the center mu. And we sample y following the Gaussian with center w in the product with xi. So for instance, if we have two Gaussian mixture component, we can generate a data set like this. So in order to generate this, let's go through the process step by step. So we first sample a mixture group, a mixture component. For instance, we sample the blue part first, and then we need to sample a mu and a w from the blue part, and the mu define the distribution of x, and the w define the slope. And for instance, if mu is 1 and w is roughly 0.8, we will sample those dots on the xy pair along the line. And I will continue to use the term task in the presentation, and the task means a pair of mu and w. So we have defined the sequence of x big K, and let's define a bit more the s small k circle plus the xk plus 1. This means we have k in context example plus an additional x. So we pre-train our next token predictor f via the following laws to obtain f star. And if we consider how do we calculate the loss, we have a decoder-only transformer, and we put the sequence x1, y1, x2, y2 into the transformer, and the x1 is corresponding to y1, x2 is corresponding to y2, and we only calculate the loss. We only calculated the loss based on y1, y2, y3, but without the x part. We ignore the loss for x part. So there are two flaws in the assumption. The first is loss is only taken on y value, and second is the data follows the format of in-context learning. So which are different from the usual pre-training of language model. But this is setting following the literature. For instance, the following paper use the setting. So after we have our pre-trained data set, we pre-train the model, and then we can perform in-context learning to predict y of x. For instance, we let the xk plus 1 equal to x, and we inference the optimal pre-trained model f star with additional k in-context demonstrations or in-context examples. And we assume those in-context examples follow in-context task mu star and w star. And mu star means the x sample from the mean mu, and w star means the y is equal to xi in the producted with w star. And I will name the w star as a function of the in-context task, or simply in-context function. And finally, we will go to the analysis and phenomenon. We will give some mathematical analysis, and we will explain the earlier sand phenomenon and forecast a bounded efficacy phenomenon. With our pre-training data set and in-context learning inference, we can show that the prediction of the input is equal to the right part, and the inner expectation is the prediction based on in-context function W. And the outside is the posterior regarding the input as observation. And moreover, in our framework, we can give closed form expression for the posterior. So give closed form expression for the outside of the expectation. And we show that if the prior of mu and W is a Gaussian mixture, and the posterior of mu and W is still a Gaussian mixture. And further, we can give closed form expression for the prediction as following. So that means our whole framework have a closed form solution, which will help us to make further analysis. So in order to explain the earlier sand phenomenon, I will give intuition here, there are theory in our paper, but here I will skip those and only explain the intuition. So for here, assuming we have two groups in the pre-training data set, and this is our in-context learning example. Under some condition, due to the X distribution similarity between the in-context task and the red group, the language model will retrieve the function roughly -1 first with few in-context example. That's a function of the red group. Since the -1 is so different, is very different from the +1 in the in-context task, so the error rate will increase. And then with many in-context example, the language model will finally learn the function of the in-context example and make the error rate decrease. And our framework can also forecast the bounded efficacy phenomenon. So in the first stage, for this case, we use in-context example with random label, and we will retrieve the desired task first, and then we learn our wrong task because the label is not the correct label. So the whole error rate will decrease and increase. We also found this phenomenon in the real-world language model in the mixture 7 billion of lemma, a bigger mixture, or GPT-4. We also provide a lot of theory of those two phenomena in our paper, but I will skip them. If you got interested by the phenomenon, you want to see the theory, please look into our paper. And thank you for your watching.